Hi, Physical Science. I wanted to go over real quick what we're covering this week really quick, which is we're going to be talking about ions this week. Okay? This word is pronounced ions. Okay? And there's actually two kinds of ions. There are positively charged ions. We call those cations. So like I said, these ones are positively positive charge. Okay. And then we have the ones that are opposite of these that are negatively charged. And those ones are called anions. Okay. Now, what do I mean by positively charged and negatively charged? So ions are just basically any of your elements that are on the periodic table, any of these guys right here. And what happened, they become an ion when they take up or lose electrons. Okay? So an ion is when an element gains or loses electrons. Okay? That's all they are. And if we remember correctly, electrons are negatively charged by themselves. So if we add those, we're adding a negative charge. And if we take them away, we're adding positive charge, basically, or losing negative charge. So what do I mean exactly by that? So a definition is easy to recite, but knowing exactly what it's saying is different. Let's start off with an example. Let's look at the example of lithium. So lithium, we know from our last unit, like our last week's talk, we know that lithium has how many valence electrons? If we look at the periodic table, lithium's right here. It's in the first column, so that means it has one valence electron. Okay, so it has one lone valence electron. Now, what is the maximum number of valence electrons lithium could have? It could have up to 8, right? Because that's the most valence electrons we can have in the outermost shell. Lithium, though, like this, so when we don't have a full valence electron shell, we say that a atom will want to gain enough electrons to either fill their valence shell or get rid of any extras that it has. Okay? So the easiest way to think about this is lithium closer to 0 valence electrons here? Or is it closer to 8? 1 valence electron is closer to 0 than it is to 8, isn't it? So by that logic, in order for lithium to be happy and have a full set of electrons in its outer layer, it will want to lose this electron and get rid of it. Because if you remember lithium's Bohr model, lithium has 3 electrons. So it has the first shell, and then it has the valence shell. It has 2 here and 1 out here. This inner shell is already full. In order for the lithium to be happy, it wants to get rid of this one. So as we can see, our electrons for ions deal with our valence electrons. So in order to be happy, lithium ditches this electron. Okay, it gets rid of it. Okay, it gets rid of 1 electron. When it does that, it loses an electron. 1 electron. That's how E minus is how I write electrons. So when we lose an electron, it's like saying minus a -1. In math, we know that a double negative means a plus, so this equals +1. Okay? Lithium, when it loses an electron, gains a charge of +1. So lithium's charge after that, it normally is at 0 because that's what a neutral atom's charge is. But afterwards, after it loses the 1 electron to be happy, it gains a +1. The overall charge it has is a +1 charge. Notice it's a positive charge. Let's go back to what we were talking about with ions and what types there are. There's cations and anions. If lithium has a +1 charge now, that means it has a positive charge, so lithium becomes a cation. Okay? Lithium, when it wants to be happy, is a cation when it loses its electron. Okay? Let's do another cation here. Let's do magnesium or beryllium. Actually, let's do beryllium. Okay? Beryllium, according to where it is on the periodic table, has a +2. It has 2 electrons. Okay, in its valence shell. So we put 1, 2. Again, in its valence shell, is 2 closer to 0 or to 8? It's going to be closer to 0, so it's easier for beryllium to get rid of these 2. It loses those 2 electrons. Okay, in order for it to be happy, because if we do the Bohr model of beryllium, it has a total of 4 electrons. The first shell has to be full, and then we have 2 out of the 8 that can go in its valence shell. It wants to ditch these 2 because it's closer to 0 than it is to 8, so it loses those 2 to have this inner shell be the only full one. Okay? Which means it loses 2 electrons. This is like saying we're minusing, so we're taking our normal 0 charge and minusing a -2 off of it. This is obviously turns into a plus, so it would have a +2 charge when it becomes an ion. This means that beryllium is also a cation. Okay? Let's look at some other ones. Let's look at the opposite side. So let's look at some anions, or like see if we can't make some of our elements over here into ions. Okay, let's look at fluorine. So fluorine, if we look at it, where it's here in column 17, which means it has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. So this is the Lewis dot for fluorine. In order for fluorine to be happy, it has to either ditch all of these electrons or it has to gain one to get to 8. Is 7 closer to 0 or to 8? It's closer to 8, isn't it? So in order for that to happen, it just picks up an electron to fill this empty space that's right here. Because, again, let's look at fluorine's Bohr model. Fluorine has 2 orbits, and it has a total of 9 electrons, so 2 here, and 7 on its outside. And it has 7 out of the 8, so it's easier for it to just gain 1 electron on here, and it would be happy. Having a full valence shell out here is called like the octet rule. Oct, obviously meaning 8. So an 8 rule, meaning you should have 8 valence electrons in here. When we add that negative electron, so it's like saying we have 0 charge to begin with because it's neutral when it's normal, and we're adding a negative 1 charge to it, which is, of course, negative 1. This means that when fluorine wants to become an ion, in other words, becoming stable with its outer electrons being full, it will be an anion with a negative 1 charge. Okay, you'll notice a lot, again, this has to do with valence electrons and filling up this outer shell or getting rid of these so that the bottom shell is full. Anions want to gain electrons and become negative, whereas cations want to lose electrons in order to become stable. So they will usually be a positive charge. Now, thankfully, you should be able to recognize that because this is like a number line where we're looking at going to 0 or 8, we can place like our number of valence electrons in order down the line and figure out which ones are going to want to become anions and which ones are wanting to become cations and losing electrons. Anything that has 1, 2, 3 valence electrons typically want to lose those because they're closer to 0 than they are to 8. Whereas those that are 5, 6, and 7 valence electrons are closer to 8 and would rather gain electrons. 4 is in the middle between 0 and 8. So the elements with 4 valence electrons can be either plus or minus. These are kind of strange because they're in the middle. But these with 1, 2, and 3 valence electrons typically are going to become cations, and those with 5, 6, and 7 will want to become anions. Okay, and if we look at how our periodic table is listed, we know that these have 1, these have 2 valence electrons, these have 3 valence electrons, 4, 5, 6, 7, and 8. So you can clearly see that on our periodic table, it's nicely set up where the elements from column 14 and over will want to create cations. They will want to lose electrons in order to become stable with their last valence shell, with their last, set of electrons. Whereas everything to the right of 14, 5, 6, and 7, all of these will want to become anions and gain electrons. Okay? And so you can see that you can actually attribute a charge to each of your family groups or your column groups here. Okay? So that's why I have up here, I have labeled that all these elements will want to have a +1 charge. All the elements here will want a +2, 3, plus -4, -3, -2, -1, and here is a 0 charge. And the reason I have a 0 charge there is because these noble gases are already at 8 valence electrons on the outside, which makes them happy no matter what. So they don't really want to, get rid of any electrons, and they don't want to gain any because they're already at a full valence shell. Okay? Does that make sense? I hope so. So, quick review. Anions and cations are just versions of elements that gain or lose electrons to fill up their valence electrons or have a completely filled outer shell. Okay? Cations want to lose electrons and become positive. Anions want to gain electrons to become negative. Elements on the left side of the table want to become cations. Those that are on the right small section of the table want to become anions. And if you notice by color, those that are metals, such as transition metals, alkali metals, and the alkali earth metals, all want to become cations by losing those extra electrons. So if it is a metal, it will want to become a cation. Whereas over here, you'll notice all of the ones that want to become anions are either metalloids or they're nonmetals. Okay? So if you have a nonmetal, it means that they want to become anions. Okay? And lastly, I want to just show you how we write those ions once they become said ions. So let's look at lithium again here. When you write lithium as an ion, it's going to look like this. You just have lithium, the symbol, with its new charge in the corner. Same with beryllium, it loses 2, so is now a positive 2 charged ion. And lastly, fluorine. Fluorine gained 1 electron with its -1 charge, now showing that it's that ion in the corner. Okay? So that's how you write your ions. That's how you find out what they are, both like longhand and by looking at the periodic table. Okay? If you have not labeled this on your periodic table yet, both the valence electron count and the charge number for your columns, I would do that now because that helps you quickly reference all of your elements very quickly. Okay? I'm going to cut things off here and I'll see you all later. All right. Bye.